Hello and welcome to this wonderful Tuesday afternoon here, streaming live from Denmark for the Azure user group and also for the Copenhagen.net user group. We have a special guest with us today, all the way from Israel. Before I welcome Oren, I just wanted to say a few things. So we do these meetups for the Azure user group and the .NET user group. Try to do once a month. So if anyone who's watching wanted to do a talk, then please feel free to reach out. And also keep an eye out for the Copenhagen Developers Festival, which is taking place in August and September, a conference by NDC. So be sure to check that out. But without further ado, please welcome Oren Eini. So just switch here so we are the same size.
Oh.
All right, welcome. And thanks for joining us. It's wonderful to have you with us.
Yeah, wonderful to be here.
All right, well, should we just kick it off and let you get started with the presentation?
Yeah, we'd love that. Yeah.
Great. I'll just add your slides to the screen and then I'll jump off. So take it away.
Okay, thank you. So I'm here to talk about scalable architecture. And this is an interesting issue because in many cases we want to have an application and build it so it can handle one user and 10 users and 100 million users and everything in between. And it turns out this isn't really that hard to do. We have the cloud, we have infinite compute capacity at our hands, no problem, right? But in order to do this in a reasonable fashion, controlling cost, complexity, and the ability to modify things as we change what the system is doing is actually really hard. What I want to focus today is some fundamental ground rules in which if we follow some relatively basic guidelines, we are in a much better position to have better scalability opportunities as the system grows and develops. So let's start from the most basic of things. What is scalability? A service is scalable if you increase resource and the performance or the amount of requests it can process in a given time frame is increased in a proportional manner. If we don't do that, then at some point we hit a limit. If we double the number of servers that we have, but only get 60% additional capacity, then we can add as many servers as we want, but eventually we hit a hard limit. And that's not a problem. We have the cloud. And we can write lambdas or zero functions, and this is now someone else's problem. And I'm happy with that. I mean, I can write my code, the company pays for whatever the cloud bill is, and we're good. Nothing else to do about that. Where's the problem? The problem here is that we've gotten quite lazy. So I want to give you this thing. What you see here is the Google. You see Google, basically. This was Google at that time frame. So it is a couple of machines, 300 megahertz, and I mean, you can't buy a phone like you can't buy a stupid phone today with those specs. And you can buy a Raspberry Pi, which has those specs for $30, $40. So what's the difference? Why could Google do so much on so little, and we're unable to do to meet reasonable scaling goals on small servers? So let's talk about what this actually means. I have some code, and Morten, would you be able to switch to the code tab? So what you can see here, and you will be, I've uploaded the slide, so you have the link for this, but this is basically a .NET implementation of Redis. This is backed by a concurrent dictionary. It's using pipes in order to do the work. And beyond that, this is about 200 lines of code, less than 200 lines of code, that implement the basics of the Redis protocol. Now, why am I showing you this? Because of one important aspect. Morten, can we go back to the slides? What you see here is this piece of code running on a Raspberry Pi, this machine on the top, and processing the Redis benchmark. You can see the details and blah, 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 blah. But what is important here is that on a Raspberry Pi, I'm able to process close to 200,000 requests per second with a latency of under 100 milliseconds for the 99% time. Now, this is me spending a couple of evenings writing some code for that. If I had a couple of weeks and I was able to unleash some of the crazy people who work here, we could probably double or triple the amount of load that we have here. And that is insane if you think about it. Because the specs of a Raspberry Pi is a quad-core 4 gigabyte. That's it. And this is basically a really, really cheap machine. You can get those for from the cloud for a few dollars a month. So how come our code doesn't meet the performance goals that we have when we're running on much better systems, on much lower load? So what's going on? So there is a very easy way to build a scalable system. You deploy the service, you figure out what you did wrong, you go back in time and rinse repeat. Now, if your time machine is broken, we need something else. So what we can do, we can look at what other people have done and see how we can optimize things based on their experiences. It's critical to understand something about that. First of all, not all scenarios are the same, and even tiny changes in the scenario can have a huge impact on the way that you're building things. What is even more important is that things change. And one of the biggest problems with scalable architecture is that as things change, you have to shift. And if you have a big system, moving a big system takes a lot of time and effort. And I'm using the example from Twitter where mentions and hashtags are all the stuff that user came up with. It's not Twitter that had designed that. They had to adapt for that. So you typically say, oh, I want a scalable system. I want to do event-driven design, CQRS, event sourcing, and whatever this is about. I like to call it the buzzword of the day because I have to chase whatever it is that is currently in fashion. And the key problem with that is that you have to deal with complexity. And complexity kills your system. It kills performance, it kills capability, and it kills the ability to make changes. So you want to try to do something simple. Simple does not mean stupid. There is a great quote, I think, by Mark Twain that says, I'm sorry this letter is so long. I didn't have the time to make it shorter. And in the same sense, if a good architecture is when you have taken out everything redundant, you're left with the core thing in its pure form without any friction or anything around that. So let's see what I'm actually talking about. First of all, the number one thing that we have to do is to define the SLA. And the SLA says something like this. What my commitment? Under what scenario? Expressed in terms that are measurable. So I like to say something like, okay, 99.99% of users should observe a page load times of under 200 milliseconds. Now, this is a nice number, it's measurable. But this is not a commitment yet, because this is a commitment when I get to say, hey, as long as we have under 5,000 users, under 50,000 users, whatever this is, because you can always add more users and the system needs to be designed for a particular load. What is important here is that the moment that we start defining the SLA, it means that we have a performance budget. How long can we spend doing a particular operation? And what do we do if we cannot meet the performance goal? If I have to do something that in some cases takes 2 minutes, how do I reflect that to the user? And now this is no longer make this faster. This is now a business concerns, a UX concerns, a lot of those sort of things. But first, we have to understand what we do. And we have to figure out, I have this limit, this SLA that I committed to. This feature cannot be done in that time frame. Or you want me to go and charge the user, I'm depending on MasterCard and Visa to process that. Something to take 5 seconds to run that. Nothing I can do about it. So this isn't a blank check to say, we cannot do that, we cannot do that, we cannot do that. The idea here is that we need to figure out how we can do things, provide scalable solution and a good responsive system for the users. So let's talk about this. First of all, the number one killer is when we don't do that and we start making expensive things. I'm going to make a call to Visa directly from the controller, for example. If I have a budget, that means that I have to be conscious of what do I spend it for. So maybe I have to go to a third party. Do I have an SLA with them that I can rely on to not be too big? Can I track that? Can I figure out what is expensive in my system? There is a huge number of DevOps tools that give us insight into what's going on. But the fourth thing that we have to do is understand that we have to commit to an SLA and work on that. Now, let's talk about what is expensive and what is cheap. It's really cheap to get something by key, by ID. If you have a simple query, if you query your local database, if you have to do some work that is bounded by a reasonable amount of, I have to update up to 5 items. Great, that's bounded, let's do that. Putting an item in a queue is super cheap. What's expensive? Almost everything else. Going to making a remote call to a third party that you don't control. Making a query that can be complex, long, involve a lot of back and forth with the database, processing a lot of data for some reason. For example, maybe the user wanted me to download an Excel file. And that requires me to go and build Excel and do some painting and graphics and whatnot. Can take a few minutes. I do not want that to happen while the user is sitting there and waiting. I want that to be defined very differently. And in general, you can see here very, very in the background, my father told me, buy low, sell high, and you get rich. And as long as we understand the relative cost of the operation that we do, we can start processing them. But that leads to just a different question. Okay, I analyzed my operations. I know that those sort of things that I'm doing are expensive. And what do I do now? I cannot not do them. That's part of the thing that I'm there to do. So the issue here is don't do the expensive things right now. Remember, it's really, really cheap to put something in a queue. And any cloud platform, Azure, Google, AWS, would have a queue that is easy, cheap, and infinitely scalable. So you can throw data into the queue very, very cheaply. Once the data is in the queue, you can start processing that. Now, a typical way of doing that would be to plug an Azure function to the queue. And now I'm in a really different place. Oh, I have some code that I need to run, which may be expensive. Go and talk to Visa, whatever that is. I've thrown that into a queue. The Azure function runtime is going to be running my code based on whatever I put in the queue. And now I have a huge amount of influx of users, whatever. That's Azure's problem. That's not my problem. It also means that all of the background work is now handled externally. And there is a very clear boundary between what I'm doing in the web application and the background stuff that happens. So it's very similar to CQRS, but the definition here isn't reads or writes. It's how expensive this is. Is this complicated? Is it unbounded in latency? Something like that. It also has a huge impact on the way that we're building things. Let's go back to the scenario that I need to generate an Excel report. Okay, I throw the report request into a queue. I have a function that go ahead and update that and generate that and does whatever code that needs to do that. And at the end of the day, I'm uploading the report to blob storage. And then I'm updating the record. Here is the requested report. Once I've done that, I've suddenly gotten myself into a really different world. Because think about what this means. Well, right now I have a queue for preparing the report. Okay, so what do I need to do? I don't, maybe, end of the month, I don't want to have tens of thousands of concurrent reports running at the same time because all of them are hitting my database and that may pull it down. So I'm saying, hey, let's define this particular function to have a concurrency of 25. Okay, I've done that. And now this is a system level configuration. What does it mean in terms of the overall system? It means that now we have the ability to say, okay, user goes in and requests a report. If there are under 25 concurrent operations going on, it will be a process immediately. Let's say it take a second or two to run. And from a UX perspective, we are showing a spinner, and here is the report. You can go ahead and download that. Perfect. What happened at the end of the month where everyone wants to generate this report? Well, it still goes to the queue. It still goes to the Lambda, but now there is a set of instances that are running and processing things. But because there is a huge amount of load, then the Lambda runtime or the Azure function runtime is actually throttling that and ensuring that the number of instances that are running isn't going to be so high that other operations will be impacted. From a UX perspective, it means that I'm showing the spinner, and after 5-10 seconds, I'm going to tell them, hey, you know what? I will let you know when it's ready. I will send you an email. I will do whatever needs to be done there. And the whole point is that the front end doesn't do much. The backend doesn't do much. It's simple. All of the complexity is in the architecture, not in your code. So what you're typically doing is just working on data that's already prepared, already chewed for you. So you can do that very, very quickly and very efficiently. So here's the issue. Why not just autoscale? I mean, I mentioned lambdas and Azure functions, and we can very easily define that, oh, I can just have more instances coming up as cheaply as that. Now, the actual problem here is that this is a huge lie. What's the lie here? I can only do this sort of autoscaling successfully if the thing that is actually limiting my scalability is compute. But we already saw that compute is cheap. A Raspberry Pi can process almost 200,000 requests per second. So compute is cheap. What is the typical scalability limits? going talking to a third-party API, for example, or talking to a database. So sure, I can auto-scale my web nodes. What happened in the backend with the database nodes? So, and scaling those is a lot more complicated, a lot more expensive. Now, I don't actually have to do that. I mean, I can use something like Cosmos DB, DynamoDB, and I'm happy. I use the serverless model and it go ahead and generate things for us. But then you realize that the way that they work is by how much capacity you're using. So if you're using, if you have a spike, and suddenly you have a lot of capacity, then a couple of things are going to happen. First of all, there's going to be a delay and additional loads while the system adjusts. And updating and scaling up database is not trivial. But more to the point, you're suddenly being hit by a huge amount of additional costs. Oh, because now you have to have much higher RCU, read the computing, read units and write units. I don't remember the actual acronym for that. So, on the other hand, if we do the limit, then with as I mentioned, with the queue and lambda or function and limit on the number of concurrency, then we have a natural way of throttling ourselves without having to hit the higher end database scaling issues. And sometimes, I mean, you can scale. Let's say I'm going to talk to Visa. Visa says, "Oh, you're charging. I'm seeing you scale up, and you're putting too much load on me. I'm shutting you down." And much, much worse, we have an issue because at the other side there is a human, and there is a clock. How patient are they? And you cannot really make it easy. Oh, let's wait another minute or two. Even 100 additional milliseconds is a huge impact on the interactivity of your system. So what happened with the queue? You put it in the queue and we process it in when we feel like it. Because, the drain rate isn't fast enough, you can add more workers. You can put in Azure functions and it will add more workers as necessary up to the limit that you have. And that means that if you have a temporary spike, then it's not going to blow through your budget. Oh, okay. Some things will take a little bit longer. I don't care. There's also another really important aspect here that's worth noting. When you use a queue, you also open yourself up for a very important optimization, the ability to actually process things in batches. Which means that instead, think about, I need to go to the store because I have to buy something for a recipe. Okay, if I'm making 3 different recipes, I go to the store once. So this is something you can do with a queue, very easy and cheaply. Another aspect is how does it actually look from the perspective of the user? Let's say that I want to write a tweet. I want to post a tweet. And I go to the website that says, hey, I just drank some coffee. Great, that's very interesting. All of my followers are really excited to hear that. And I hit enter and it immediately show up on my browser. Does not mean that it immediately published. First of all, Twitter needs to probably look at the image that says, is this a cup of coffee or is this a cup of tea? We're not allowing tea in the platform. We need to verify that, who of your followers actually interested enough to see that, or much of other work that needs to be done. So the distinction here is that I submit the operation and I get confirmation that it was accepted. In the case of Twitter, they just show it to me as if it was already in the website. It's easy and cheap. There is no big issue with me seeing my own tweets. From the perspective of other things, sometimes just I have to make an actual distinction. Okay, I accepted this operation, I completed this operation successfully, unsuccessfully, etc. But just these very small things of building the UI in asynchronous manner or expecting asynchronicity has a huge impact on your ability to actually scale as time goes by. Okay, so I already mentioned batches because that reduces the per batch overhead. And we can actually start doing more interesting things. I don't want to use a queue. I want to use multiple. But why is that? Because for Brazil, I have to use a special, relatively annoying address validation routine. And I have to go and talk to an unreliable third party. I want to segregate that portion at the infrastructure level. So all of the distinctions on different behaviors and patterns are now distinct, so I can scale them out separately. Oh, I know that typically I'm going to allow up to 25 function instances for charging Visa, but if I'm using EU Pay, I have a much higher limit, so I'm accepting for that 100 concurrent instances, stuff like that. The other aspect is that this also creates a really strong separation in your system. Your code only process input, output. A message is the input, whatever output you have is that, and that's it. There is no UI concern, there is no mixing of the layers, any of those sort of things. It also means that you don't have any shared state to deal with. There's no session, caching, the user authentication, all those sort of things are out of scope. We are dealing with pure backend operations and how they are working. Okay, now, what happens if there is an error? With a queue, that's easy. We just put the message back we put just the message back directly in the queue, and we reprocess it again. There is some caveats around, I need to make sure that they don't stall on this message and move it to the dead letter queue, etc. But it's really simple. If I want to update my code, okay, spin a new worker, deploy a new function instance, and that's about it. And the really nice thing about queues is that from an operational perspective, they are trivial. They don't do much, and that is a huge multiplier in flexibility and ability to understand. It also gives you a lot of really interesting metrics. How much time do my messages spend in the queue? How fast am I draining them out? What's going on right now? I see that we have a lot of messages. Let's see what exactly is going on. By the way, I forgot to mention, but in here, you can log all of the queues so you can look at what happened in the past. It generates an audit trail and make it easier to understand what's happening in your system. You should note about privacy. And if you're putting sensitive information into the queue, that may cause you to limit how long you retain that and those sort of things. But just in general, this is a very powerful abstraction. Now, in the front end, I'm dealing with stuff that's really prepared by the backend. And most of the things that I'm doing are really, really cheap. Mostly concerned with, here is the data that I have. Go ahead and do that. If I have an action that isn't cheap, it's going in the queue, and there is a UX challenge to actually do that. Now, if the user experience don't attempt to promise, I can do this report very, very quickly, do it inline, then it is a huge difference. How many orders do I have in my system? Here are the results. This report is accurate as of 9 a.m. today. Now, you may want to run it every 5 minutes, but the fact that you're explicitly saying this is what the result is as of this time frame give you a huge amount of freedom. Going back to the need to update, it means that I can take down the workers, the function instances, and nothing breaks. The queue gets bigger, but I will deploy the new instance in a bit, and it will take care of that. So again, make things a lot simpler to deal with. Now, let's talk about what happens when we have more complicated stuff. a huge multiplier, a huge superpower that you can use is that you have a cache. Now, I'm not talking here about a cache in the sense of a memcached or something like that. I'm talking about something like Cloudflare, CDN, or something like that. The idea here is that we structure our application to rely on the cache being there. So let's take as a good example a news website. We have frequent changes in content, and we also need to offer personalization. How can I reconcile those two requirements together? Well, the way that it works is that I plan for that upfront. So look at this. I have this set of stories, and this is just a JSON endpoint that gives me the story and just details. And those are behind the CDN. Those are cache. And even if I have 1 minute, 30 seconds of cache timeline there, that still means that now scalability is someone else's problem. Even if this changes all the time, then okay, then the Cloudflare would ping me once every 30 seconds. It would ping me 10 times a second, whatever. That's not a scaling issue. Here's the results. Now give it to everyone else that needs them. And it's going to cache that for 1 minute, but that still reduces in an amazing fashion how much I need to deal with. There are also other things that, I can cache it closer to the user, blah, 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 but that's the basic. Now, how about this? This one is for a particular user. And I may have many users. But the idea here is that this changes very rarely. So I can also cache that. Maybe I would push update to this directly, maybe not, doesn't actually matter. So at the UI level, the first thing that at the front end, here's what I'm going to do. I'm going to say, give me the channels that these users are interested in. This is how I do personalization. Given those channels, let's go and fetch the latest news from all of the channels that you care about and do the mix-up at the client side. I get personalization, I get really, really fast system, and I get to lean on someone else's infrastructure. That gives me a huge amount of freedom. It's not my complexity, it's someone else. And that means that I have a huge level to deal with. Another thing is that we wait. We explicitly go to a mode of, this is not something I can complete immediately, throw it in the queue. Make it explicit to the user, this is going to require wait. Even if most cases, it says, we expect that to usually close in 10 seconds. Okay, sure, Speeder, say it's accepted, and we'll handle it shortly enough. The key here is that under edge cases, super low, something happened, whatever, you can slip the timeline because they're not active. They are familiar with, I can go away and come back later to have these results. Okay. Now, another aspect is just say sorry. What do you mean by that? I want to sell you something. Okay. I'm going to accept all of the orders as soon as possible. I'm going to tell them, hey, I accepted that. What happened if I run out of inventory? Sorry, here's your refund. Been designing things so you can say sorry. So the operation is reversible, has a huge impact. Now, this assumes that you can do that. For example, if you want to buy a plane ticket, how would the airline handle that? Surely there is a fixed number of seats in the plane. They would very happily take your money, give you a seat to a full flight. And what happens is that they rely on the fact that Some people will cancel the flight, some people will no show, and worst come to worst, we have a full flight and we have too many people. Okay, here's $100. You're going to take the next flight, or something of this nature. So, being able, from a business perspective, to make this sort of operations has a huge impact on how you can scale. Because now you don't have to, for each order, to have some globally consistent structure. Now, the problem is that you're not always able to do that. I want to sell the Mona Lisa. There is one such item. As you can imagine, a lot of people want to buy it. Well, that's really, really easy for me to handle. How do I do that? Well, I'm saying, here is your bid. And I'm just putting that in a queue. And I'm telling you, I got your bid. You did not win. I got your bid. And afterward, we're going to say, hey, let's get all of the bids that we want. Let's sort them by the amount, and let's get a winner. Now, at this point, this is really, really important. I don't have concurrency. If someone is complaining, I have the audit log. I want to run some complicated business rules that needs to do a whole bunch of stuff. No problem. I'm good with that. And I have the time to do that because of the way that we structure the overall architecture of the system. Another aspect, and you might see me harping on that, being stupid. Your front end, the customer-facing stuff is as stupid as possible. Oh, I render a JSON file, the headers, the stories, the headlines, the sports, fashion, whatever. It's trivial to scale that. The simpler you make things, the easier your ability to actually lean on existing solutions. The moment you have complicated solutions, you're going to have custom solutions. So the moment you have a complex processes, you have to have custom solutions in order to scale them. And if you can just copy paste the solution for, I know how to do that, we've done it 100 times, that's great. Then your front end is simple, your application in general becomes much easier. And most of the complexity now is infrastructure. That's not your concern. So here's another aspect. Let's say that we have an invoice scanning up. So how do we do that? Well, the idea here is that the user says, I want to upload an image, an invoice. We give them a pre-send URL, and they upload that directly from their app to blob storage. We have a trigger there that would run image recognition. We put the output of the image recognition into a queue, and then we associate that with the right employee. Notice that for a large portion of the time, I have no code. Again, linear infrastructure to do that. And that means that I'm not paying for a servers to run, I'm not paying for a function, megabyte per second, etc. It does mean that you have a more complicated system because now you have discrete pieces. So this is something that I would only go for if you have a direct need, and something like, I can directly lean on infrastructure to do that is one of those cases. Okay. This is trivial. One of the reasons PHP is so popular is that there is a limit to the complexity that you have. You run the page, there is no state between pages, there is nothing really that interesting going on, and you have the ability to do that. If our frontend is mostly like that, read some data from the DB with cheap queries, show it to the user and you're done, and anything else handled elsewhere, then you're almost guaranteed to have a really, really fast system. And it's almost guaranteed to be able to actually scale it up and scale it out very easily. It's I think that right now the Tech and Power benchmarks are something like 7 million requests per second. So there is on one server. And you cannot really do wrong in this case. Because it's simple, it's trivial. Oh, I need a cache. I'm throwing a cache behind that. Give me 30 seconds. My concerns are gone. And with that, we have some time for questions.
Yeah. So we haven't had many people write questions in the chat, but I have one. Something I was wondering about when I saw the presentation. So I mean, I very much agree with your point about having the infrastructure handle the complexity. But I feel like that every time I have discussions with people about using something like Azure functions or Lambda functions in AWS, that people worry about login to some extent. Like, okay, so now we're stuck with Azure for this part, or we're stuck with Azure because we use Cosmos DB, and it's not trivial to go and use something else if we decide that. So I'm curious what your opinion on that is.
Well, a lot of that depends on what do you expect to actually move. Moving cloud platform is not a trivial thing to do. It's kind of complicated. Now, if your code is mostly about message passing and the complicated pieces, the background bits, they accept the message, they process that and put it somewhere else, then you already have some degree of separation from the cloud. There is an easy way to isolate the Azure runtime and the Lambda runtime. So you have, here is a message, input, output, and that's it. That also makes testing things a lot easier. But in practice, the sort of things that you are stuck on for migration is not, oh, I'm using Lambdas or Azure functions. Is, oh wait, I deploy my system and now I have built a lot of monitoring, observability, behavior around that. Those are the things that are much more expensive to move. If you're using something like Cosmos, then you're marrying the platform unless you want to do a more expensive migration. There are options for all of those to have a cloud abstraction layer. And I mentioned Azure and Lambdas as an example, but you also have a OpenWhisk, and you can run those sort of behaviors on premise as well. And the most important bit about that, by the way, is that what I just described already created a very strong separation between the pieces in the system. You have the front end and the back end. And the front and the back ends don't talk directly to one another. They'll go to a queue or the database, something like that. You should be able to take your front end, schlep it to another location, and start using it there. And oh yeah, I may have to pay additional fees to egress some data from the front end to the back end between clouds or something like that. But that's not that big a deal usually. And you also have the ability to say, oh, I have 30 lambdas that I'm using. Let's convert them one at a time. And the conversion process says, okay, let's take lambda A and let's write it as a Azure function. Let's update the lambda A definition to take the message, write it to the Azure queue on the other cloud. And now you have the ability to do that while the system is running with no interruption in service and all of the usual things around that.
Yeah, that's a good point.
Yeah.
I guess also some of the flexibility that you get is also saving you in other parts of what you're developing, right? So you can use something that's almost plug and play and then have an immediate benefit instead of kind of reinventing the wheel just to be not locked into something.
Something that is important to also remember is a complexity of the solution as a whole. So even if I have, I mentioned 30 lambdas, Okay, that's a lot. Trying to understand how all of those pieces go together, deploying them, that can be complicated. In some cases, you may want to say, "Oh, I'm just going to," especially if you want to go to a more complicated infrastructure concerns. Oh, I'm using different queues and I'm maybe pulling from multiple queues at the same time. Those sort of things. At the same time, what I found is that generally moving between cloud platforms is either a requirement from the get-go, and then you use something like Kubernetes abstraction layer and Kubeless
Yeah,
or something. So this is already done for you at this level. Or I'm running on Azure, and I know that I got this huge deal from Microsoft, and I'm going to be running it for at least the next 5 years. I'm not changing.
yeah,
And just accept that and make the best of that, because otherwise you're at the lowest common denominator, and that sucks.
yeah, yeah. Yeah, so we just had a comment from another Morten who just wrote nice and simple because everyone in
Awesome.
Denmark is called Morten. Every other guy. No.
Yeah.
Yeah. Also, no other questions, but so I'm curious about another thing that you mentioned in your
Mhm.
presentation about yeah, the fact that it's difficult to scale databases, or when you can use the queues to ingest, and then
Mhm.
you can get a lot of ingestions in, but you still have some concerns or some potential bottlenecks in terms of the database. So I think the point you made was about possibly using the front end, or maybe using something like SignalR to push out updates so you get immediate visibility. But
Mhm.
are there some other tips or tricks
Yeah.
to deal with databases? Like
So
if you have a
mhm.
business that wants, like if you're publishing something and they want it to be as instant as possible, but obviously there's some constraints in the system.
So let's talk about what is the input of that. A database can either be really, really simple, show me the latest post from Oren, or can be these hundreds of lines of SQL, or that has to touch 10 different tables and indexes or something like that. Uh, for the front end, from everything that user is, when I'm talking about front end, I'm talking about the user is sitting there waiting for it to happen, then you want to have only as simple queries as possible. For anything that's more complicated, throw it in the backend, do it in the background, so you can limit the associated cost. Oh, I know that this is an expensive report. Let's limit to maximum of 10 items at a time. And now I'm doing that by utilizing the cloud infrastructure to say, oh, just 10 instances of this function, stuff like that. But hello,
Yep,
can you
you're
hear
still
me?
here. Yes.
Okay, my monitors went dark, so I'm not seeing anything.
Okay,
But
you're still here.
okay, that's really funny. Okay, I'm back fully. So the story then is that how do you scale a database? If you just do very simple things, then it's relatively easy. Oh, I have a big disk, fast machine, something like that. The moment that you start, oh, I now need to query over a lot of data, and now my working set is impacted or something like that, then that's become a lot tougher. Especially because when we're talking about the front-end queries, they tend to be really simple and follow a predictable pattern, and the back-end queries tend to be a lot more expensive. You can scale a database in one of a few ways. One of them is get a bigger machine, bigger disk, faster disk, and disk are an enormous latency hog for databases because they always read and write from them. Or you can have replicas, and with replicas, that means that you have to think about, okay, what is the consistency between them? So there are well-established solutions for all of those. But the underlying issue is that I don't want to go there. I want to go with the approach of, okay, I have a database that is really simple. I hit it. It's trivial to run the operation to optimize them properly, and then I have background things that happen in the background. And the front-end queries also. Oh, I see that I'm seeing a lot of cost here. Put the front-end queries behind the cache. Even for 5 seconds, that has a huge impact. And that's something that I can do because now I'm not guaranteed. Now, if I want to respond to events, the Excel that you wanted is done, so I want to push that to Signal now, again, I'm going to be using cloud infrastructure for that, not my own code, not my own solution that I have to build and maintain. So there is hubs on Azure. I don't remember the actual name. There is a SNS on AWS, and all of those can manage that for you. There is a caveat that some of them are charging on per message basis, and we may need to worry about billing for that. But for the most part, they tend to be cheap enough that it just doesn't matter. And again, relying on someone else to do that is a lot easier. That's it. And I see that Mikel is saying that the queue is always a solution for scalable architecture. And the answer is sort of. A queue in the middle gives you a lot more freedom, but you have to also design a system to actually take advantage of that. So you're not making those promises that you have to keep afterward. That's a key aspect here.
Yeah, and then there was a comment from Oren again. Using the materialized view design pattern goes well with the architecture that Oren laid out.
Yeah, absolutely.
Yeah, but I think that was it. I don't see any other questions popping up, so I think we can end it here. Okay. So I'll just again say thank you so much for the presentation. Lots of good insights, lots of good points. So really appreciate it that you took the time to talk to us today.
Okay, that's wonderful. Thank you very much.
Cool.
Thank you for having me.
Yeah, of course. And I will just end the broadcast.